Hello, welcome to NXP's Quick Learning. I'm Stephen Waterhouse. I'm a concept engineer at NXP, and I'm going to discuss reverse recovery and diode leakage in switch mode power supplies. As demand for higher efficient power supplies has been going up over recent years, this has resulted in a requirement from the market for lower switching losses, reduced gate charge, faster switching frequency and reduced dead time. And because of all these, we've resulted in very fast switching MOSFETs. The problem is with some of these fast switching MOSFETs, this can cause problems within the design if it's poor layout or if it's some other design constraints. And this could include phase ringing resulting in EMI, gate glitch which could result in false turn on of a MOSFET, ending up in shoot through, and we could end up with burnt out devices. Many people within the industry believe that Schottky diodes within the MOSFET are the solution to this. And if we look at the benefits of including a Schottky diode within the MOSFET, we can look at the reverse recovery waveforms. On this waveform we've got two timing aspects to the reverse recovery. We've got TA and TB. And we've got another parameter which is the IRM. So ideally what you want from the MOSFET with a Schottky diode is for as low as possible IRM as you can get. So you want this to be as low as possible, you don't want it to go too far, and then you want a nice long smooth recovery in this TB portion of the switching waveform. Normally we'd expect to see a parameter known as the S factor, and this is TB divided by TA, and for good switching soft recovery performance we say the S factor has got to be greater than 1. These are the benefits of the Schottky diode within the MOSFET, but there's also some disadvantages, and these relate to the leakage current. If we look at the IDSS leakage, as a manufacturer, it's a parameter that we use to measure whether there's defects in the silicon or in the process as we manufacture our products. So we measure IDSS to screen defects in devices. And what we know is that an integrated Schottky masks these defects because it has a much higher IDSS. And also at hot temperatures, we know that the IDSS leakage is even worse for a Schottky device. These are problems for a semiconductor manufacturer. We want to be able to measure defects within our silicon, our products and our processes. What this means for the customer is it could lead to early life fails. We could have poor quality of MOSFET, which would affect the quality of our customers' products. In battery applications, we could drain the battery when the device isn't even switched on. And if we're having problems measuring defects in our silicon because of leakage, then we know that our customers could have problems testing in their application as well. So then we have to widen their spec to acceptable levels to cater for the leakage. And the last one is the effect on efficiency, and this is down to power loss or temperature rise within the circuit due to those this leakage through the MOSFET. I've put a chart up here which explains the leakage in the MOSFET and the Schottky. So if we look at the green trace, this is for a typical MOSFET, and we can see that the IDSS leakage there is fairly low, and as we get towards its breakdown voltage it starts to ramp up until it gets into avalanche. If we look at the red trace, that's for a Schottky diode. We can see that already starts off at quite a higher leakage level, and that's maintained all the way through, and that's at several orders of magnitude above the MOSFET, and that'll have a slightly higher breakdown voltage before it goes into avalanche. And the black trace is for a MOSFET with an integrated Schottky. It takes the worst of both, so it takes the IDSS leakage of the Schottky, and then when you get to the MOSFET you get to its breakdown voltage, and that's where the avalanche occurs. Our Nexperia products, we've got this Schottky performance without this leakage. So the leakage performance of our Nexperia S3 products are per the normal MOSFET. So we'll follow the green line. It allows us to screen at a lower level so that we can measure defects, and for the integrated solution you'd have to measure there, and that's a bigger window to allow defects through to the application. For more information, go to nxp.com/NextPowerS3. I look forward to speaking on the next Quick Learning.